Okay, welcome everybody to the bsac weekly seminars. Many of you have been here as regulars, and maybe some of you are new, but we have a weekly seminar where we have people from academia as well as industry come and talk to us on a wide range of topics. And today I think you'll hopefully be blown away as much as I was several years ago when I first heard about this new technology. Welcome to the seminar. So our guest today is Professor Yuan Cao from actually here at Berkeley. So he's a new professor here at Berkeley. He joined us from Harvard in the EECS department here. He got his PhD from MIT, and his primary research interest, which you'll hear a lot about today, is in the electrical, optical, and mechanical properties of low dimensional materials. So low dimensional meaning less than 3. And also how to engineer those properties and some of the applications that he's exploring the use for. He will also talk a little bit about MEMS. He uses MEMS, I think, and maybe these materials might be helpful for some applications in that space. He's won many awards and prizes, which I'm sure many of you are aware of. And I won't go through all of these, but he's been presented awards from Nature magazine, Time magazine, a lot of prestigious awards that he's received. But without further ado, I'll introduce Yuan to all of you, and thank you for coming today.
Okay, thank you for the excellent introduction. Welcome everyone to come into my talk, and it's my honor to present at the bsac seminar here. So, today I'll be talking about our recent research on, this real-time twisting. So what are we twisting? We're twisting these 2D materials, as you can see, up in the corner that has this kind of little twist between two kind of lattices of materials. And but before that, let me first kind of give you a short introduction of what are 2D materials and why we are interested in them. So in one sentence, why we want this lower dimension is because lower dimensions give us more tunability. And I'll give you an example to show you, what that means by more tunability. Nature gave us a lot of these materials that can be classified by their, for example, electrical properties, whether they're insulators or conductors, or superconductors that are things that conduct without any resistivity, or magnetic properties as well. And it turns out that you can thin down these materials to their monolayer limits, which means material with 1 atom thick. And those materials still retain these properties of the kind of bulky forms. For example, there is this material called hexavalent boron nitride, HBN, that is a one atom thick insulator, and it's actually one of the most the best insulator existing in the world. And you probably know about graphene, which is a very well-known material, and it is a good electroconductor, and among many other fantastic properties in this material. And there is also 2D forms of superconductors and magnets that I won't go into detail. Now we just see that you can make these 3-dimensional or bulky form materials into their 2-dimensional counterparts. But now, what are the benefits? If you just take graphene, for example, we know one way of graphene, and you can simply put a metal gate beneath it, and it is basically effectively something similar to a MOSFET that you're more familiar to that than I do, but. And you can put a gate voltage between them. You can change the carrier densities or charge density inside the system. And for graphene, you get this kind of Dirac-Cohn-like dispersion relationship, and which means that when you change the gate voltage, you get this V-shaped like conductivity curve. And at the charge neutrality, it is a material with relatively low conductivity, and you can add a gate voltage to tune its conductivity, and so on and so forth. And if you change graphene to a different 2D material, like MOS2, then you can get a real MOSFET with a large on-off ratio, and so on and so forth. But all of these rely on basically the fact that the 2D materials, the charge density can be tuned very easily just by putting a nearby gate, and you don't need to dope it. You don't need to do chemical doping. These are all electrostatic gating. And that was one of the easiest tunabilities in 2D materials. But we want more in these materials. And one of the most intriguing discovery in these 2D materials is that you can modify its properties also by twisting. And what it means that, okay, if you look at 2 layers of graphene here, well, I just have 2 layers of graphene that is one is red and one is blue, and they're stacked on each other. If I put a little twist between them, you start to see these, long-range modulations of the lattice, which is known as the Moiré pattern. And they occur because there is a lattice mismatch between the two, lattice vectors when you have a small twist in them. Now, this seemingly simple operation is actually a very powerful knob for tuning the properties of these materials. And it turns out that we can change graphene, which, as I showed, is a very good electrical conductor. But by putting down a little twist, we can change it into either an insulator or metal, or also superconductor and magnets in certain conditions. And that's really intriguing because we're kind of creating these kind of novel phases of matter seemingly out of nothing, but just by this twisting. So what happens when you twist 2 layers of graphene is that, at this specific angle called the magic angle, when the 2 layers are twisted by 1.1 degrees, the electrons in graphene, they do not move in the Dirac cone that I showed you before anymore, but instead they form these so-called flat bands. And well, if you recall that the velocity of electron is related to well, the slope of these energy bands in the momentum space. So having this flat band really means that electrons become very slow in the lattice. And if you do some numerical simulations, you find that they're actually getting kind of almost stuck at this so-called AA spot, where the two, well, it's like the brighter spots in these Moiré patterns. And when the electron behave like stuck in real space, then they behave fundamentally different. And as a result, we're seeing these kind of really intriguing phenomena, including superconductivity, which is state with 0 electrical resistance. And for example, these occur at really low temperatures, like this is 2 kelvins. But below that temperature, the resistivity become absolutely 0, and you can measure that just by just measuring the 4-pole resistance of this device. And again, this is really astonishing because, well, in carbon, or any form of carbon, including 2D form of carbon, which is graphene, superconductivity has never been observed before this. So we're really creating this new phase of matter just by twisting, and that's why it was put out pretty shocking discovery at the time in about 2018 during my PhD. And after this discovery, there has been a lot of research in this front, and there has been a lot of new scientific discoveries in these twisted materials, both in graphene and in other 2D materials as well. And some examples are shown here, and I won't go into detail, but this kind of fractional quantum non-toy is one example that was very popular and also brought a lot of attention since last year. And now, if you bring some analogy to these 2D materials, you can think of photonic structures, certain photonic structure like photonic crystals, also like a quasi 2-dimensional system, like basically a thin dielectric layer with a lot of holes in them. And there has also been kind of commensurate research in this front, where you can twist 2 sheets of these kind of photonic crystals or other nanophotonic structures to tune their properties via these twisting effects. But now, I put a lot of hype here, but I want to also say that there are some caveats of this twisting that I haven't mentioned to you yet. So I try to frame it as if twisting is as good as gating, but it's not, at least yet. Well, the main reason is that when we make these twisted, samples, either of graphene or any other 2D materials, once you put down the 2D materials together and they're stuck, you cannot change their twist angle anymore. So it's kind of a one-shot process. And you make that device. And if you want to change the twist angle, you have to make another device. And actually, that's what we've been doing so far in this field of studying these mooring materials. For example, if I want to study, let's say, superconductivity, what's the temperature for the superconductivity as a function of the twist angle. Then what I need to do is basically I need to make tons of devices, tens of devices, or even 100 devices. And then, I try to sort of get some trend out of these many data. So, there are two problems here. One is, well, it's very challenging to make 100 devices, of course. And second thing is, well, different devices have different behaviors. So, it's always hard to get a consistent, scientific result from, across a broad spectrum devices. So, is there a possibility of doing an in situ twisting, meaning that, if it would be very nice if we can change the twist angle in situ so that you can avoid all these problems. And I think this would be future of this, Mori field if, we want to also thinking of building actual functional devices and finding some applications for them. And now what is the challenge in doing this? Well, you might think that 2D materials are fragile, but actually they're not. Well, even a one atom thick material, it is, including graphene, is very robust, and you can, suspend it on hold and you can poke it, or you can, apply some pressure and bubble it. It won't break. Up to some point. And it's very strong compared to normal materials that we see in daily life. You can do also kind of funny things like stretch shading, like as an origami, kirigami. And recently there are also some research that uses a AFM, which is atomic force microscope, to push these 2D materials to try to achieve some sort of rotation motion. But all of this technique, it rely on this atomic force microscope, which is basically a kind of a nanoscopic tip that you can kind of scan over the sample and achieve some sort of a nanomechanical manipulation of the 2D materials. But these systems are usually pretty complicated, complex, and pretty big. So it's really not what we want if we think about putting twisting as something on par with electrical gating. So we really want to have the twisting something that is just as easy, as user friendly, and also as cost effectively as electrical gating. I just want to put a gate voltage. I just want to put down some voltage or some knob like that, and I want to be able to twist 2D materials. Is that possible? So that's the problem we want to solve, and here is the solution that we kind of proposed. A MEMS-based structure. So these are nanostructure or nanoscale materials. We want to use a small device to manipulate it. That's my original motivation for doing this. And MEMS is the perfect choice for this purpose. So what we have is a device like this, where it has 2 degree of freedom. One is let's start from here. One is kind of a vertical translation, and the other one is the rotation. And well, these are all actuated by electrostatic actuators, so both the vertical and the rotational one. And well, these are all kind of via flexural suspension, so there is no hysteresis and things like that. So this is a platform that we designed from the scratch to be able to study twisted 2D materials. So they are it's fabricated purely from silicon, both the device and the handle layer. And now, because we want to study these 2D materials, one of the things we want to be able to achieve is to operate this device at any temperature or magnetic fields, because these are often, well, these are things that are required to seeing those scientific discoveries in these materials. So we actually tested these devices down to 4 Kelvin, and it works perfectly fine because well, these are electrostatic devices, and there's nothing really limiting its operating temperature. So now where do we put down the 2D materials? So on the back side of the device, we have fabricated this kind of protrusion of a pyramid just by anisotropic silicon etching. And now what we can do is kind of tenting a 2D materials just like on a pyramid. So you can put down 2D material just on this tip. And it will kind of look approximately like that. So you have a piece of 2D material on the tip on this MEMS device. And I have another 2D material on a substrate, and this substrate, well, it can be any material, but we're using it with, we're making it with, basically a glass wafer. And then we put these two chips together and bond them by an SU8 spacer. And now if you, drive the device layer of the MEMS device up or down, or rotating it on the axis, then you're basically changing the distance and the twist angle between the 2D materials, or or effectively you have a device. If you zoom into the tip, it will be something like that. So so one 2D material is tented, the other one is flat, and then you can change their spacing and the twist angle as well. So the benefit of this device is that firstly, by design, it is very flat. So, this is actually pretty important for manipulating 2D interfaces. It has to be very clean. There can't be, junk or anything. It has to be very flat because otherwise you're getting, one side to be touching, the other side doesn't touch, so you don't get the properties you want. And the other, important things we want is accessibility. So, this substrate is transparent, so we can do all sorts of optical experiment onto these 2D materials, and this is both useful for categorization and also studying their properties at low temperature and so on and so forth. And this is not really possible if you think about the previous ways of doing twisting in situ, like using atomic force microscopes. It's like a bulky thing, and you can't really easily put up some light into it. And this is what a real device looks like. So it's about 1 centimeter in size. So it is a very compact device, and we can compare to the atomic force microscope, which is a bulky device, and we can in principle integrate these devices into any scientific instruments or low temperature apparatus and things like that. And I'll briefly kind of comment what it takes to make these devices. Well, so our starting point is, of course, this industry standard silicon insulator wafers, and we first make the tip on the backside just using the KOH etching, and then we develop this kind of special process for doing a in situ through silicon vias just from the device to the handle layer. And the reason for doing this is to kind of achieve the complicated function without needing external wires or things like that. So we can, it's kind of basically we can design like a in situ kind of mini PCB, like 2-layer PCB from top to bottom layer, and achieve like these complicated functions. And then we do the Bosch etching from the backside and also the top side, and then we release it using vapor HF. So and these constitute the different layers as you see here, the device and the handle layer, and how the silicon pillar in the middle is used for putting down the 2D material. And these are some videos of how these devices operating in real time. So first you're seeing the rotation, which is driving the 3-phase electrostatic actuators, just ABC, like in order. So there are 3 sets of electrodes here, and they achieve the rotation. And the vertical motion is another electrostatic actuator, and you can see the moving out of plane. That's why you're seeing it's kind of getting in and out of focus in the microscope. And finally, this is the picture of an actual device where we have 2 layers of 2D materials. So one is on the pyramid, that's the black one. And the other one is this semi-transparent one. That's the one on the flat substrate. And we turn on the electrostatic motors. You can see one layer rotate against the other. Okay, and if you compare, this device which we call Mega 2D, and I think it's a synonym for something. Compare it with the atomic force microscope based technique that I kind of briefly described just now. Well, the main advantage is that this Mega 2D device is very versatile, meaning that it can be operated in any environment, and also we can make these devices in batches because it's on a standard 6-inch wafer process right now. And the only limitation we really kind of have is the range. So with these kind of electrostatic MEMS devices, we can achieve something on the range on the order of plus minus 12 degrees for rotation. And this is kind of plenty for studying graphene, for example. If you recall, we only need 1.1 degrees to reach the magic angle. But of course, it would be nice if it can just freely rotate, and especially these 2D materials, they usually have a kind of hexagonal structure, right? So if you can rotate 60 degrees, then you can kind of cover the entire practice space for studying these materials. And we are right now working on the next generation of this device, which allow us to twist plus minus 30 degrees, which will be 60 degrees in total. And now I want to kind of show you what we have so far done and what we can potentially do with these new devices we developed. So in this study we are basically using this hexagonal boron nitride, which you recall is a excellent electrical insulator, but it's also a kind of interesting optical material because it has kind of interesting nonlinear properties. So which means that if we shine a red light into the system, a femtosecond laser, like if you focus on the HBN, it will generate a blue light by this process called second harmonic generation. So it doubles the fraction of the light because the hexagon boron nitride breaks some internal symmetry, and we can use that process to monitor the operation of these MEMS devices. So this kind of shows the experimental scheme here. So basically, we have 2 layers of hexagon boron nitride, just as I showed you in the video. We have one on the one tented on the pyramid, and the other one just flat. And we're shining in a femtosecond laser from the transparent side, and we're monitoring the generation of blue light from the red light in this experiment. So as you can see here, we're changing the voltage on the z-axis actuator, which brings the 2 layers of HPN closer or farther apart. And as we're doing that, we're seeing this kind of oscillation in the second harmonic generation signal. So what that means is that you're seeing this kind of oscillation, right? And this is really kind of a characteristic of the kind of mini optical cavity that is formed between the 2 layers. So it's kind of a fabric parallel cavity as we are moving the 2 layers closer apart. And the period between these oscillations actually correspond exactly to half of the wavelength of the laser we use to excite this system. So that would be 390 nanometers. So we can use this to precisely calibrate the MEMS device, because now we kind of can convert the voltage we apply onto the electrostatic actuator to the gap between the 2 sheets of 2D materials. And what you can see is that after these kind of 4 oscillations, the signal kind of settles to a constant value and doesn't change anymore with the voltage we apply onto the MEMS actuator. And that basically means that the 2 sheets of 2D materials are now in contact, so they cannot move anymore. So this is basically like a sanity check that this device is working as expected, and we're getting a good interface between the two 2D materials. Now, in order to see that, we can also kind of look at this map of the second harmonic generation. So the square in the middle is basically the size of the silicon pyramid where we put down the 2D material. And this map is showing you the, oops, press something. It is showing you the a map of the second harmonic generation. We can scan the laser across the sample and seeing which part or which point generates second harmonic generation stronger or weaker. And the lower left shows the corresponding optical image of the device. And this is before we bring the two sheets of HBN into contact. And now the second one shows when we bring into the contact, you're showing you're seeing kind of a little bit of inhomogeneity here. Like for example, this spot is brighter and this spot is a little bit darker. And that's because when you put two sheets of 2D material close by just like that, well, it tends to trap some air or some junk between them. And that's just the nature of these 2D materials. But what we can do is that we can like let them remain contact and then we twist and twist. And what that does is it would actually squeeze out the trapped air and junk if you do this kind of a few times. And indeed, after doing that, what we're seeing is that the interface become much more uniform and cleaner. So this is also known as the self-cleaning mechanism for 2D materials, because these 2D materials, they are atomically flat interface, and kind of they really likes to be intimately contacted. But if there's some trapped air, then it cannot get the intimate contact. But after you kind of squeeze it, like it has a tendency to squeeze out the dirt on itself, and get a cleaner contact just by itself. So now if you follow the field of 2D materials a little bit, kind of this stack of 2D materials, whether it's 2 layers or more layers, it's usually known as the van der Waals stack. And this is because, well, there is not really any bonding between these 2D materials. The only thing that kind of stick them together is the van der Waals force, which kind of the universal force between any flat sheets of plates. And it's also actually why we can do this kind of twisting in the first place. If you think of kind of bulky materials formed by chemical bonds, usually it's kind of a legal block, right? Like you can only kind of snap these legal pieces at certain orientation. Like if you think of growing epitaxial semiconductors on the interface, you can only grow it when the lattice is matching, and so there are these kind of requirements when working with bulky materials. But for 2D materials, because they are bonded by this van der Waals force, it means that you can put down 2D materials at any angle without needing to worry about lattice mismatch and those things. But usually when we talk about these van der Waals materials, you don't really think about the van der Waals force itself. But and that's because usually you don't have a easy way of measuring these kind of forces between these two materials. But with this kind of mega 2D device, we can actually do that. And this will show you, when we apply the electrostatic motor, kind of get into contact, and then we remove the voltage, there will be a hysteresis before the interface start to move. And that's because there is a van der Waals traction between the two interfaces. So you first have to overcome the van der Waals force, and then the interface would all of a sudden jump to some distance. And that's what we're seeing here in these kind of measurement of the second harmonic generation. When we scan the voltage, back and forth and back and forth. So we're seeing this reproducible hysteresis loop. And from that, the size of that loop, we can calculate and estimate what is the van der Waals traction. So it's estimated to be about 4 megapascal in this device. Okay, so far we haven't really started to use the rotating part of the MEMS device, right? So now let's look at that. So first thing I want to mention is that these twisting materials, they are intrinsically handed or chiral. That's the term that physicists like to use, which means that if you twist two sheets of material to one direction, it's actually the mirror image of twisting to the other direction. It's like kind of left and right hand, and they are not totally equivalent. And that's especially true if you think about the optical properties. So usually the a beam of light we think of is polarization, right? It can be linearly polarized, but it can also be circularly polarized, like left circular polarized or right circular polarized. And this circular polarized light is also handed in nature, right? It's left. That's why it's called left and right hand, circularized, polarized. And now, if you shine a left-handed polarized light onto this kind of twisted structure, well, because let's say it's the left side one, then it will behave differently if you shine a beam of left-handed light to the right-hand structure. So left to left, left to right, they are different. And this is known as circular dichroism, meaning that the optical response of the material to left and right circular polarized will be different if the material breaks the handed symmetry, or it has like left or right handedness. Now this actually has been measured quite a while ago in this this is actually twisted by the graphene. That's the one that I showed you in the introduction. So it shows you that so what is plotting in the y-axis, that's the circular dichroism. That's the basically difference in optical reflectance of left and right-handed circular polarized light. And different curves are different twist angles. So each black curve is basically the left-handed structure. Each gray curve is the right-handed structure, and you're seeing that they have opposite signs if you measure its circular dichroism. And if this is for a mirror symmetric structure like no handedness, then the signal will be zero. Okay. But now you see that this measurement was done with many samples. So each curve is basically a different sample, because you have to make a different sample to get a different twist angle for twisted biography. But now we don't have to do this. Now we have this new mega 2D technology, and we can measure this circular dichroism of this kind of symmetry breaking just in one device. And the result is shown here. So here we are seeing we're showing in the color the circular dichroism of the second harmonic generation. So basically how much second harmonic generation is generated, the difference between the second harmonic generation between left and right-handed circular polarization. And what we're seeing here is that as you change the twist angle, at 0 degrees, you're not seeing, well, it's basically all white, so meaning that there is no circular dichroism. But as you twist by a twist angle to the left or a twist angle to the right, you're seeing opposite signs of the circular dichroism in second harmonic generation. It's perfectly antisymmetric with respect to 0 degrees, just as expected. So I want to get a little bit deeper into the nonlinear optics in these 2D materials. When you have a sheet of HBN, and if you shining a linear polarized light to excite the second harmonic generation, the light you get out is also linearly polarized. Okay. But if the HBN is twisted by some angle theta, then the outcome of this second harmonic generation is also rotated by an angle that equals to 3 times the twist angle. Okay, and the number 3 here comes from the fact that these materials are C3 symmetric. So it's if you rotate the system by 120 degrees, it is exactly the same as before. And there is a name for physicists. It's called like Pankrathen battery phase for this kind of nonlinear process. So we're seeing that by changing the twist angle, or by changing the angle of this one sheet of HBN, we're changing basically its polarization. Okay, and now if you think of a system have two layers of HPN, and I'm rotating one layer with respect to the other one. Then I'm changing the relative polarization between the second harmonic generation from the first layer, which have like one polarization, and the second layer, which have a different polarization that is rotated by 3 times the twist angle, right? Okay. And now if we can also think about the other degree of freedom that we have in the system, which is controlling the displacement between the two 2D materials, right? And that's what we call displacement H. And this one is simple because as you change the distance, you basically change the relative optical phase between the two, the light that comes from the first layer and light from the second layer, right? Just by this phase factor that is proportional to the, wave vector of the light. So now what if we use this theta, the twist angle, and the displacement H, kind of in conjunction? I just tune them together because these are the knobs we have in this system. And we can kind of use them as this kind of so-called synthetic space. So if you just imagine these two knobs as now two kind of coordinates in a kind of virtual space. And we can actually see that these virtual spaces have some pretty cool properties. So this color map shows you kind of basically the polarization of the light that is generated as a function of these two variables, the H and the theta, for two layers of HPN. So we continuously tune both the interlayer spacing and the twist angle, right? And each spot shows you the polarization. And there are these kind of peculiar singularities in them. So actually, there are many of them. There are 4 of them in this space. And what happens is that, okay, so if I start with this point and the system generates a linear polarized light, then if I move my system around it, like just by changing H and theta, just go around that singularity, well, the polarization of outcoming light rotates by 180 degrees. Okay. And now if I look at another point here down there, then the polarization will rotate on the other direction for 180 degrees. Okay. Now there are actually some deep physics rules for these singularities I won't go into. But what happens if I put my system to be exactly on this spot? And what happens is that it would now generate circular polarized light. So this is kind of funny because we're putting down a linear polarized light, but what it generates is a circular polarized light. And this is again because the system has intrinsic handedness. So it's intrinsically breaking the left and right-handed symmetry. So we can now generate this kind of circular polarized light just out of nothing. And now these are kind of theoretical explanation, but we can actually verify all of this in a actual mega 2D sample, and we can actually continuously tune these two knobs of changing the twist angle and the H, so we can actually see these singularities, and it's actually analogous to this so-called Maron and anti-Maron in physics. So one potential application that we think that we have for this system is to build this kind of polarizational tunable light source. So the idea is that now basically we have a tunable system that we have some knobs on it, right? Just think of some gears, like you can rotate it. And now if we put in a fixed polarization light, like a linear polarized light, the output can actually be in arbitrary polarization. So an arbitrary polarization is usually represented on this so-called Poincare sphere, where each of the 6 endpoints of this sphere represent either linear polarized light or circular polarized light on the top and the bottom of this sphere. Okay. And this is because around one of these kind of singularities I mentioned earlier, the polarization of the light is highly sensitive, and well, it's rather complicated, but it's very sensitive to the change in H and the theta, the twist angle. So just by playing these two knobs within a small range, we can change the polarization to any polarization we want. And some examples are shown here. So this up polarization, this is vertical polarization, this is horizontal polarization. These are the 45-degree polarization, and this is the left circular and right circular polarized light. So you can see that we can almost cover the entire, Poincare sphere just by playing with the, spacing h and the rotation theta. And this is done without changing the input, right? The input is fixed. It's just a fixed, linear polarization. And we're only changing the h and theta, which are internal to this interface. And now by analogy, we also have a quantum version of this device. So, and this just basically, using the nonlinear optical properties in reverse, basically. So, just now we're shining in like, 2 photons of, red wavelength, and we're generating 1 photon from the blue wavelength. This second harmonic generation, you're doubling the frequency of the light. But there's an inverse process, which is called the spontaneous down conversion. And basically you're shining a blue light in just 1 photon, and then the nonlinear optical property would automatically split it into 2 photons that are in the red wavelength. And the nice thing is that the generated photons are entangled, which means that you kind of cannot specify what are the exact polarization for these generated photons. They're kind of quantum entanglements, kind of a quantum superposition of up, vertical and parallel. Vertical and horizontal. So with this device of Mega 2D, then what we can do is basically generating these entangled photon pairs that have both tunable entanglement and the polarization of the entanglement. So if you overlay into this previous Poincare sphere that I'm showing, basically now you can show a similar sphere where the top of the sphere is a quantum state with no entanglement, whereas the state on the equators are this kind of quantum superposition of up vertical plus horizontal, or horizontal vertical plus vertical horizontal. So that's the these are the possible polarization of the 2 photons that come out of the system, and when they're entangled, then you cannot tell exactly what polarization they have, but but they are correlated in a kind of quantum way. And I think that would be all that I want to talk about today. So if you're interested in this new technology that we developed, you can read our paper that appeared on Nature about 2 months ago. And there's also a report by the Berkeley Engineering News with nice graphics. And with that, I would like to thank the great people that work with me on this project, including those at Harvard and MIT and Stanford. And well, special thanks to Dr. Colin Tang, which is make great contributions and all the hard work in this project. Yeah, and if you have any questions, I would like to happy to answer them.
Yeah, we have questions.
Yes, thanks for the talk. I'm wondering, so in your Mega 2D, the top device layer, you have a very stringent flatness requirement. I'm wondering for your substrate, you have the SUA spacer. How do you make the SUA spacer as flat?
So SU8 is, if spin coated, then the SU8 is supposed to be flat within maybe tens of nanometers at least, right? So the device is about I guess 6 millimeters in dimension. So if you're just tilting it by tens of nanometers, it's like basically not tilting that much. So I mean that's within the flatness requirement that we have. So we're saying the flatness is 0.01 degrees, right? So that's definitely within that range. Yeah.
Thank you for the talk. So you have this pyramid that holds onto the 2D material, right? I'm wondering if that pyramid sticking out is causes problems for the material and if there's a way to not have a pyramid sticking out. So
Yeah, that's a very good question. Well, so having a pyramid have definitely many advantages. Oh, one thing is, well, if you just have two pieces of two materials with large area, they're stuck. Yeah, then you kind of can't pull them apart again. So you basically you want to only have a limited area of contact, while the other part are not contacting, and then they're supporting it, kind of clamping it to the not touching area, like the higher the or the taller area in this place. So you want to anchor them there and only have this small area of contact so you can pull them apart. Yeah. Yes.
Yeah, I have a question. Curious about if you, for example, if you don't only take the two layers, you have more layers, you have more degrees of freedom. What will happen? You can it provide more tunability?
Well, definitely yes. And then for this kind of nonlinear optics, we actually working on this. So if you have more layers, you can for example, you can also tune which direction you can generate the light and so on and so forth. But it's kind of challenging to do this right now because well, you can imagine if you want to have three layers, maybe you can just have one device from the top and one device from the bottom. That's possible. I don't know how to work with more than three layers. Yeah. Yes.
Well, how difficult is it actually catch or like, are you limited to like one material per wafer, or you dice it up for the sequence? Different materials per run? Yeah, how is the like kind of?
Also, each device, each. Oh, okay. So the question is, well, if I understand correctly, whether we can, well, how we are making this device, chip by chip. Is that the question?
So really, it's more so so you make one wafer of all these metal
Yes.
boxes. Are you able to use different beauty materials for each wafer, or is it limited to like, okay, for this wafer I will use one
Okay.
set of materials,
Yeah.
like I just thinking maybe you can dice it up, or I don't know how is that?
Okay, I guess just repeat your question. You're asking if we just limit it to one material per wafer, or we can use different material for each chip, right?
Sure.
Yeah. Okay. Yeah, we can use also. Yeah, these devices are automatically diced up after releasing. So after release, it just falls down to each chip. So yes, we can use different materials for each chip. So so far these 2D materials they are exfoliated, meaning that you kind of use this kind of old school tape material technique to prepare small pieces of 2D materials. And we use kind of this polymer assisted transfer to transfer them onto the tip of the pyramid. So yes, we directly transfer onto the pyramid. Yeah. So we can transfer any material that we want. Yeah. Yes.
This is an amazing experiments that you have done. I'm wondering what is the most challenging step of the whole experiment? Is the MEMS portion, or attachment, or assembly of the 2D materials, or the measurement?
So I would say, well, this kind of through silicon vias was very challenging well, it took a long time to figure out how to do this appropriately. And putting down 2D material is challenging, but well, we've worked on 2D material for a long time, so we know how to do these transfers. So that's actually not too bad. Yeah. But getting a clean and reproducible pyramid, flat and clean pyramid, that's also difficult. Yes.
How big is the pyramid area?
So we can make anything from a sharp tip to like something with a flat top that has like 10 micron or something like that. But we're currently using so yeah, the current size is about 4 microns. So there's a scale bar here. Yeah.
You have
Yeah.
some ideas to scale this up to more than
Sorry, can you repeat?
Do you have some ideas or some plans to scale this up?
Scale this up.
Yeah, to more than 2 centimeters.
Well, I guess yes, possibly. Well, we can make larger MEMS devices, but I guess the question is what is the purpose of scaling up? So if you want to get a larger contact area between the two 2D materials, then we can already do that without scaling up the device, right? These are that's not the size of the MEMS is not the limiting factor for the contact area between these 2D materials. Yeah.
But a follow-up question to that is as the contact area changes, how does that change your characteristics that you're measuring?
So that's something that we're actually not sure. So I would imagine that as you get a larger area, then it will be more difficult to pull it apart. Right?
But I mean, the electrical or optical properties, how would they maybe change aside from the mechanical ones? That you're
I don't think that should be changed fundamentally. Well, so right now we're shining a focused laser beam that probes only half a micron or 1 micron of the device. So yeah, and you can see that for example, this is a optical property over the area of the pyramid, and it's kind of more or less uniform.
Optically, I'm just wondering about electrostatic or magnetic properties that are bigger. I'm wondering if that contact area would change the response to electrical field, or magnetic field, or something.
Okay, that's something to be studied. Yeah,
just curious.
Yes.
How do you control the issue?
Yeah, that's a very good question. So
repeat the question.
Okay, the question is how do we control the initial angle between the two materials? So for HBN, we can determine its lattice orientation also by second harmonic generation. So we basically first pre-screen these kind of flakes that we exfoliated to know their lattice orientations, and then when we put them onto the mega 2D or the substrate, we kind of already know the orientation, so we can align them under microscope so that initially they are close to 0 degrees. It's not exact, but within a few degrees that's possible. And the rest we just use the mega 2D to cover the range of twist. Yeah. Yes.
So you are transferring the flex to the MEMS.
Yes.
Pyramid. From what I understand from my previous, when you transfer those flags, you are more or less
Yes.
And when you do this kind of experiment, I'm wondering whether that strength will actually affect the results.
Yeah. So we actually
question again.
Okay. The question is if there is effect of strength after putting down these 2D materials and how they affect our measurements. So we actually studied this kind of in quite detail because many people asked us about this, we can actually measure the strength in this HBN just using atomic force microscope, and we find the strength is actually pretty controlled. It's usually on the order of or less than 0.3% or something like that. And I think it is also that's actually an advantage of the pyramid. So yes, there will be some strength, but it is kind of a controlled strength that is kind of given by the protrusions of the pyramid. Yeah, and that's actually better compared to usually in 2D materials when you stack things together, you cannot control the strength. It's just whatever that is brought in by the polymer that you use for transfer it. Yeah. Yes. Okay, the question is how do we make sure the two layers of 2D material are parallel to each other? So, 2D materials is intrinsically flat, right? It's atomically flat. So, and basically the only thing we want to make sure is the basically the only thing we want to make sure is that the bottom of the pyramid, silicon pyramid, is flat with respect to the substrate, right? The 2D material themselves, and we just assume it to be flat because it's supposed to be flat. So there are two aspects to this. So first is the pyramid bottom has to be flat with respect to the MEMS chip itself, and that's usually easy to guarantee because these are etched by KOH, right? So if you have a uniform etch rate, then the top of the pyramid is supposed to be flat with the rest of the chip, right? I mean, the chip is also the chip has to be flat from the start, and that's just guaranteed by the quality of the wafer, I guess, which is supposed to be flat, within, I guess, a few nanometers on this size, I think. And the other thing is, as someone already asked, the SU8 spacer has to be flat, right? So I think if these are, flat enough, then the flatness between the 2D material and the substrate is guaranteed. And we can actually measure that flatness just by, doing some interferometry between the pyramid and the substrate. So you can actually, well, so if you look just from the microscope, the color actually changes as you change the distance between the two, the MEMS and the substrate. From that color, you can estimate how much tilt you have. Right? Yeah, this is from interference of light.
Okay, one last question. Okay, go ahead.
Yes.
So as far as I understand, you are using the mega structure to mechanically increase the
Yeah.
Are you considering using this mega structure also using it as a kind of to electrical properties of the material?
That's part of the next plan. Yes. Well, so currently we are doing this experiment. It's all, optical experiment, right? And we haven't, used the electrical part yet. Yeah.
Yeah, it's interesting. Yeah.